Welcome to my video lecture. This is an Amarnath, Assistant Professor in Mathematics, MLR Institute of Technology, Hyderabad. Under the course Linear Algebra and Calculus, we are dealing an important topic, Cayley-Hamilton theorem. The part 2 video continues to the previous one. Previous lecture, we have done what is Cayley-Hamilton theorem and its statement and applications of Cayley-Hamilton theorem, such as finding inverse and powers of a matrix, like that A inverse we can find, A square we can find, A cube we can find, A power minus 2. This type of higher powers and inverses we can find using Cayley-Hamilton theorem. That was done in the last class, and present lecture we are going to do some more applications, that is such as polynomial degree of a matrix. Means such as sometimes the expression will be given for a matrix in terms of A cube minus 3A square plus 4A. This type of expressions will be given. Then questions will be asked on this expression. Express a linear polynomial, or find A power 8, or express in some other values. So, that all are applications of the Cayley-Hamilton theorem. Let us do the problems on this one. So, here is a problem. He given a matrix, 2 by 2 matrix is given, and he is asking to write the polynomial. So, this is a polynomial of the matrix 2A power 5 minus 3A power 4 plus A square minus 4A as a linear polynomial in A. What do you mean by linear polynomial? Means degree 1 polynomial. Degree 1 polynomial. Now, what is the given degree polynomial? This is a 5th degree polynomial, because highest degree of the A is 5. So, that is why this is 5th degree polynomial is given. And what is asking to express in as a linear polynomial at a degree 1 polynomial, means only in terms of A, that we want using Cayley-Hamilton theorem. It is an application of the Cayley-Hamilton theorem. So, Cayley-Hamilton theorem, what is the statement of the Cayley-Hamilton theorem? Every square matrix A satisfies its own characteristic equation, that we have discussed in the last lecture. Now, using that concept, we are going to answer this one. Let us do this problem now. So, we need a characteristic equation. So, the given matrix A is equal to 3, 1, minus 1, 2. So, we need to write the characteristic equation. The characteristic equation. The characteristic equation of A is det of A minus lambda I is equal to 0. We know very well this equation. Means det of A minus lambda I means the determinant of the matrix. From the diagonal element of the given matrix, we have to subtract the lambda, that is the A minus lambda I. Means the first diagonal element 3, just you write minus lambda, remaining element as it is, 1 as it is, and minus 1 as it is. Second diagonal element 2, subtract minus lambda. So, that is a determinant. So, determinant, do not write the bracket here. So, that is a clearly we need to write 1 and det, which is equal to 0. This is det of A minus lambda is equal to 0. Simply from the diagonal element 3 minus lambda, 2 minus lambda, remaining 2 elements 0. We are discussing from the eigenvalues and eigenvectors topic. So, this is a determinant of 2 by 2. So, how to find determinant of 2 by 2? AD minus BC, 3 minus lambda into 2 minus lambda minus of minus plus 1 is equal to 0, right. This one we are simplifying. So, multiply and write 3 into 2, 6 minus 3 lambda minus 2 lambda plus lambda square plus 1 is equal to 0. So, simplifying starting from highest degree, lambda square minus 3 lambda minus 2 lambda minus 5 lambda, 6 plus 1, 7 is equal to 0. This is a characteristic equation of the given matrix A. Now, as per Cayley-Hamilton theorem, the square matrix A has to satisfy this equation. What does it mean? The lambda will be replaced by A. So, that is a according to Cayley-Hamilton theorem. According to Cayley-Hamilton theorem, right, lambda will be replaced by A, that is called satisfying the characteristic equation. Now, so this equation becomes where lambda square means it will become A square minus 5 lambda minus 5A plus 7 is a constant. Constant cannot be added to the matrices. So, the last class we have discussed, that is 7 should be multiplied by I, so that all 3 will become matrices. We can add it according to Cayley-Hamilton theorem. So, this is a main equation. From this equation, we need to get the above polynomial 2a power 5 minus 3a square plus a square minus 4i, we have to change in terms of first degree. Now, here what I will do, every higher degree term I will write in the linear, means a square in terms of a is in power 1, but a complete expression we want in a. So, a square, a cube, a power 4, a power 5, these all terms will be written in terms of a. Now, first time I am writing a square. What is the a square value? Take to other side, plus 5a minus 7i. This is a square value in terms of linear polynomial a. Now, let us take a cube. So, multiply by a cube. So, multiply by a to get the a cube on both sides, a square into a cube, 5a into a square, 5a square minus 7a into I, that is a. Okay, now this above equation I am multiply by a, multiply by a. So, we know very well a square into a cube, a into a square, I into a. Any matrix is multiplied by identity matrix, we get the same matrix, right, 5a square minus 7i. But a cube also we want in linear polynomial. So, already we have a square in linear polynomial, replace a square, which is equal to 5 into a square value is 5a minus 7i minus 7a. Okay. Now, finally, a cube is equal to 5 into 5, 25a, 25a minus 7a, that is 18a, right, minus 5 into 7, 35i. This is the a cube value in terms of a, which is in linear polynomial. Again multiply by a, because we want all higher powers, a power 4, a power 5, everything we want, multiply by a, that is a power 4, which is equal to multiply by 18a into a, 18a square minus 35 I into a. I into a means again it is a only, 35a. It is a second degree, I want as a linear degree. The question is linear polynomial in a. So, a square again we will replace. So, already we have a square value 5a minus 7i, right, minus 35a. Now, simplifying, finally, a power 4 value 18 into 5, 90, 90 minus 35, that is 55a, minus 18 into 7, that is 126i. Okay, a power 4 value 55a minus 126i, a power 4. So, a square is a linear, a cube is a linear, a power 4 is linear. Then, I want a power 5 also. The given equation polynomial contains a power 5 is the highest degree. Again multiply by a. This equation a power 4 equation multiply by a. Okay, right. So, that I am going to write in the next slide, that is a power 5. So, we are multiplying a power 4 with a power 5, 55 a into a square minus 126 I into a, that is a. So, above equation a power 4 multiplied by a at 55 a square, 126 I into a, that is 126 a. But it is a second degree a square, that also should be replaced, which is equal to 55 a square. So, a square value already we have in terms of a, that is 5a minus 7i, which we have earlier. So, from this one simplifying, a power 5 value minus here 126a. So, a square I am replacing minus 126a. Finally, simplifying this 55 into 5 minus 126, finally we will get, that is 149a, subtracting a terms, and the 55 into 7, that is minus 385i. This is a power 5. Now, we got all a square, a cube, a power 4, a power 5 in terms of a only. I is treated as like a constant, it is not the polynomial of a, just I is a constant. Now, given problem at a given polynomial, right, given equation, that is 2a power 5 minus 3 a power 4 plus a square minus 4i, that we are replacing in the linear polynomial, that is equal to 2 into a power 5. So, we have 149a minus 385i. Next, minus 3a power 4. What is the a power 4 value? Earlier we have in the slide, that is 55a minus 126i. Next, a square value 5a minus 7i. Next, minus 4i, right? A power 5, what we replace? A power 5, a power 4, a square in terms of linear polynomial in a, that we expressed, because already we have prepared all the values using Cayley-Hamilton theorem. Now, simplifying all these, what are all these terms here? A terms, here a term, here a term, here a term, all a terms, and I terms, here I coefficients. So, simplifying that, we are going to get 138 a minus 403 I. This is a given polynomial in terms of a linear polynomial. It is a clearly linear polynomial. Linear in the sense first degree polynomial in A. Linear polynomial in A. That is a required answer. Okay, linear polynomial in A. So, in this case, we are finding the given fifth degree polynomial, we are writing as a linear polynomial. This is application of Cayley-Hamilton theorem, right. Next, we are going to do one more problem here, that is, here is asking to find, using Cayley-Hamilton theorem, find a power 8 if a is equal to 1 to 2 minus 1. Here he has given a 2 cross 2 matrix. So, a power 8, generally if you want to find a power 8, how to find a power 8? A into a into a into a into a, that is 8 times you have to multiply, very typical calculation part. But using the Cayley-Hamilton theorem, we can find this type of higher powers very easily. Let us do that one, how to find them. So, we know what is the equation of the Cayley-Hamilton theorem. The characteristic equation satisfies the square matrix, satisfies the Cayley-Hamilton theorem, that is the characteristic equation. The characteristic equation of A. So, whenever we are using Cayley-Hamilton theorem, we have to take the characteristic equation is det of A minus lambda I is equal to 0. Earlier we have done, and here also we are doing, right. So, how to do this one? From, it is a determinant line. So, from the diagonal subtract the 1 lambda, 1 minus lambda, 2 minus 1 minus lambda. Okay. Means diagonal, from the diagonal element subtract the lambda, remaining elements no change. So, every time we are doing. So, AD minus with determinant expansion, 1 minus lambda into minus 1 minus lambda minus 2 into 2 minus 4 is equal to 0, right. This equation multiply and simplify, 1 into minus 1 minus lambda into minus 1 plus lambda minus lambda into minus lambda, lambda square minus 4 is equal to 0, right. Lambda square, next plus lambda minus lambda gets cancelled, minus 4 minus 1 minus 5, which is equal to 0. So, this is a characteristic equation of given matrix. Now, here according to Cayley-Hamilton theorem, square matrix A satisfies above characteristic equation, we know very well. So, according to Cayley-Hamilton theorem, so lambda will be replaced by A, that is satisfying the equation, that is the meaning. A square minus 5 constant will be multiplied by I, because A square is a matrix, 5 is a constant. A constant cannot be added to the matrix. So, that is why 5 will be multiplied by I according to Cayley-Hamilton theorem. So, I want, he is asking to find A power 8. So, I am separating A square from this equation. So, what is the A square value from this equation? That is 5I. And I want A power 8, that is A power 8. So, required one. a power 8. A power 8 means we can write as a square whole power 4 we can write. 2 into 4, 8. So, that is equal to a square value from the Cayley-Hamilton theorem we got 5i whole power 4, right. So, this is a square into a square into a square 4 times, or a square power 4 and a 5i directly power 4. So, that we know very well how much that is 5 power 4, 625. I power 4, what is I power 4? I identity matrix, how many times you multiply you will get again I only, I into I square into I power 4, any values, that is 625. So, this is a value of a power 8. Right. So, a power 8 625, that we can conclude the value. So, a 8 times you want to multiply, that is a typical. Here in this case we are finding a power 8 or a polynomial, we are expressing different problems we can do. So, these are the applications of Cayley-Hamilton theorem, right. So, here I am providing some problems to practice. So, here as a matrix 2 by 2 matrix is given, express this polynomial as a linear polynomial. We have done in the first slide a similar problem, and one more problem here, one more polynomial is given, is asking to find the value of this much big polynomial. Generally finding a power 8, these all terms are very typical. Then using Cayley-Hamilton theorem, simply we will get a polynomial and we will find the higher powers of a, and directly we can add. So, these two problems the student can practice. So, in this session what we have done, that is applications of Cayley-Hamilton theorem, that is a linear polynomial problem we have done. Any higher degree polynomials are given, we can express as a linear polynomial. And in the next class we are going to discuss about the diagonalization of a matrix, continuation to the eigenvalues, eigenvectors, and Cayley-Hamilton theorem, one of the important topic, diagonalization. Okay. So, that's all my lecture. Thank you.